are going to continue our discussion on model based collaborative filtering, and specifically in today's lecture we are going to talk about basic latent factor models. So, these are the concepts to be covered. First we will talk about baseline predictor, then we will be talking about SBD, enhanced baseline predictor, which also is popularly called as SBD latent factor model. Then we are going to talk about SBD++, where along with the rating matrix we will also be considering some kind of implicit feedback. To start with, collaborative filtering models capture the interaction between user and item. So, how this interaction is captured? By the rating matrix. So, to both model based as well as neighborhood based approach, the rating matrix is the input. Now, from this rating matrix we tried finding out the similarities and made the models that we called as the neighborhood based models. Then in model based approach, instead of using some heuristics like that of creating the similarity matrix and so on, we tried building the models. So, that from that model itself, when a new user comes and looks at a few other items, then we can provide some kind of rating prediction. Now, when in one of the earlier lecture, I have also told you that this rating matrix can have many kind of bias. Specifically for users, there will be bias. Some users will be very high raters and some will be always giving the low values, and over the time it may vary, and the items themselves, some items are likely to get higher rating compared to the others. So, all these biases we are going to capture, then we have to build models accordingly. The first model, that is popularly known as baseline predictor or baseline estimator, goes like this. Here this is the rating, predicted rating, and mu is the mean of the overall rating. So, if you consider a typical rating matrix, there will be many users, there will be many items, and there will be specific rating values. Even if it is not full, it is sparse, still then also there will be rating matrix, there will be ratings. Now, mu is the average of such ratings. Total number of ratings observed, sum of that divided by the total number of rating. Now, Bu is the observed deviation with respect to user u, and Bi is the observed deviation with respect to item I. Suppose mu is 3, Bu is estimated. So far we have not estimated. Assume that we have already estimated this value, and Bu is 0.34 and Bi turns out to be minus 0.23. So, therefore, the predicted rating as per this particular model will be 3.11. Now, the next question is, for mu it is fine, we can take the average, but how do we estimate the biases with respect to user and the item? So, that is the next question we are going to look at in our next slide. So, if our observed rating is RUI, what is U? U is the user, I is the item, and if we consider all the ratings which are visible to us, which means all the pairs of UI for which rating is available, let it belong to set K. So, set K contains what? All the valid user item pairs for which the rating value is available. So, this was, as per our model, this was BUI, Okay. So, RU minus this estimated value plus what is this term? This is the regularization parameter. So, this is the actual error with respect to the biases, this is the regularization parameter. Now, we can solve this particular problem, this optimization problem, and find out the values of BUs and BIs. So, how many BUs we are going to find out? As the number of users in the system. How many BIs? As the number of items in the system. Now, look at this. How do we solve this? To solve this problem, this is the problem. To solve this, we have how many unknowns we have? Total number of BUs are same as number of users, and this is number of items. So, if number of users are m and number of items are n, so total m plus n number of variables you have whose value you would like to determine. So, therefore, what will be the typical approach? You will be taking the partial derivatives with respect to each of these variables, setting it to 0. You can do it together to run gradient descent algorithm, or you can do it individually to run stochastic gradient descent. However, we can even simplify the situation further. So, if you simplify the situation further, then we are going to shortly see, if we consider only if we assume all the BUs to be known, then we get the model in terms of only BI, and the value of BI turns out to be this. How it turns out to be this, that will be seen shortly. Then for each user U, we can replace this value of BI over here, and again solving it in terms of BU, we can find it out. Now, let us move ahead and see how to solve it. Now, initially, as I said, we set all the BUs to be 0. So, if we set all the BUs to be 0, then with respect to BI, how many BIs are there? We still have many variables. How many BIs? We still have n number of BIs, because m users, m number of BUs and n number of BIs. So, we now take the partial derivative with respect to one of the BI. So, if we take the partial derivative with respect to one of the BI, then with respect to the other terms, it naturally other terms will be treated as will not be considered, they will be treated as constants and they will not be okay. So, here actually this would have been the partial derivative. So, you will be taking the partial derivative with respect to each BI, set them to 0. So, when you set them to 0, with this one if you set to 0, BI is going to come to this side and this one is going to go to this side up, and here we have two terms, BI plus lambda BI. Of course, 2 is going to be going away because you are setting it to 0. So, BI, so lambda, from here lambda is coming. Now, this BI, how many? So, this is same as that of summed over 1 with respect to this particular set K. What set contains? K contains. The set K contains all the user item, available user item pairs. So, with respect to I, how many unique I's are there? So, that makes that number is this one. So, similarly, once we find out these I's, then we will be putting these BI's, we will be putting with respect to the original equation. Original equation is this one. So, here we will assume mu is known, bi's are estimated. Now value of bu, this will also be known. So now what remains? This one and this one, and where these bi values are already estimated. So this we put this value, and the moving going in the same manner that we did here, we take the partial derivative of E with respect to bu, a specific bu, and from this we set to 0, and from this we determine, just like we did it here, similar manner we can find out the values of bu. Now in this baseline predictor, what was the idea? The idea was rating reflects three things: the average behavior of how users rate the items, that is represented by mu, then users bias and item bias. Now here in this new model, it considers that not only user bias and item bias, we can also include the latent factor corresponding to users and items. So to remind you, what are the latent factors? This concept of latent factor was coming from singular value decomposition, which was simplified to UV decomposition, and from UV decomposition we know that U matrix was representing user factors and V matrix was representing item factors. Okay. So now in this U and V matrix, if we consider, then a specific rating which is given by user U on item I, this considers the factor corresponding to user U and the latent factor of user item I. Now what is user U? Suppose you consider certain k number of factors. So this pu basically is a vector, pu1, pu2 up to pu k, small k, and qi was again having the terms qi1 to qik. So here also k latent factors, here also k latent factors, and you multiply these two. So this q, I mean all of, if considering both of them to be column vectors, here I wrote as row vectors. So this is, so considering them as column vectors, you multiply q transpose, that is this one, with p, that is the corresponding column vector, and if you multiply you get these terms. And when we consider, look, this is the regularization term, this is the regularization term for what? For items, how many items? The total number of items available, and how many users? Total number of users available here. So now for this item I and U, both these are vectors. So when you take norm of this, basically what you are doing, individual elements, you are taking the square and adding them up. Here also individual elements you are taking and squaring and adding them up. So this is the L2 norm of these two vectors. Okay. So now moving ahead, what is the strategy now? We are supposed to find out the solution to all these values of all these parameters. How do we do it? Again we go for gradient descent or stochastic gradient descent. In gradient descent, all the elements at a time you will try to find out the partial derivative with respect to all the terms, and in case of stochastic gradient descent, one at a time. So, considering that we are moving ahead with stochastic gradient descent, let us just see with respect to, if we would like to modify Bi, what is going to be the corresponding error term. Okay, so this is our RUI cap. This RUI cap or RUI hat is the estimated value, and suppose we increment. What is our aim? Our aim is, if we start with certain random Bi, in the next iteration we will be making Bi plus some delta Bi, right. So, let that delta Bi be here. So, this original equation with respect to now Bi is getting incremented by this delta Bi, and moving ahead, if we, this is simplified, and moving ahead, when we take the partial derivative with respect to delta Bi, so delta Bi turns out to be this. So, this simplification, this because we are taking it with respect to delta Bi, rest of the terms are going to be assumed to be constant. So, naturally derivative with respect to them will become 0. So, automatically you will be getting, this is gone, Bu is gone, only this Bi will remain because delta Bi is getting multiplied here. So, consequently you have this, in which with delta Bi this is also and what is this term? What is this term? This is the error term. This is the error term. Where from the error term is this. Okay. So, though we have seen it, we did it for only this one. So, similarly, this parameter update equations for rest of the parameters can be determined in this manner. So, how many such values will be there? There will be m such values, and here n such Bi's, and here how many? N number of items with k features each, this many parameters, and here how many? M number of users into k number of features. Okay. So, that is how you will be, and every time in the first iteration this was the value, this was the estimated value, this difference turns out to be the error. Second iteration again this will be the, you will be re-estimating this error. So, you will keep on updating. So, you start with certain random values of this parameter and you keep updating following these equations and follow this stochastic gradient descent algorithm. In fact, this stochastic gradient algorithms last lecture we have seen with respect to only latent factor models where these biases were not considered. Now, we extend this idea of SBD. What was SBD in this context? SBD was that baseline predictor where latent factors were also considered. That was popularly in is called as the SBD based model, SBD based latent factor model. So, that model we are now going to extend. How will you extend it? So, we will extend it by considering certain implicit feedback. If you remember, what is implicit feedback? Rating is something which the user explicitly gives, and implicit feedback is something which has to be collected by observing the user's activity. So, it is here one very nice, actually before, in the beginning I should have told you, if you remember in one of the earlier lecture we were talking about the Netflix competition. So, all these models were developed by a team from the Bell Lab, and those team of 3 people, 3 researchers, they tried developing all these models. So, as we move ahead starting from baseline, then SBD, SBD plus plus and so on, this is basically mostly the contribution of these 3 researchers. So, in SBD++, what we are going to do? We are going to consider this implicit feedback matrix. Now, this implicit feedback matrix can be generated by observing the behavior. In the absence of such external implicit feedback, you can get it from the user rating. So, it can be derived from user rating. So, if you do that, the model turns out to be like this. Item feature remains same, but users feature model, latent feature model gets enhanced by, this was the original PU and this is the additional term, this is the additional term. Okay. So, here in this term yi is the factor vector rating for jth item user, for the jth item from user's perspective, and Ru is the set of items rated by user u, and R, this is the total number, this is the set, this is the number of elements in that set. Now, the question is, why do we get it in this form? So, this you have to remember, because in few next lecture also we are going to encounter with this term. This is one example how SBD++ is derived, we can derive implicit feedback from the rating matrix. Suppose this is our rating matrix. Wherever there is question mark, those places are blank, rating is not available. Now, we can construct a implicit feedback matrix from this. So, this feedback concept behind this feedback matrix F goes like this. If user has given some rating, then let it be 1, at least he has considered giving rating, and if the rating is not available, then make it 0. So, that is how here 1 rating, here it is -1, here it is 1, here it is 1, here it is 2, only this place rating was not available. So, we make it 0. So we repeat the same thing for all the rows. So, after we repeat all the rows, then we try making the normalized feedback matrix. How do we normalize it? Take all the elements over here, take the square, take the root over and divide that. So, it is normalized so that L2 norm of each row is 1. L2 norm of each row remains 1. So, we divide this by, this is 1, 2, 3, 4, 5. So, sum square of all the ones is 1 again, and take the root over, so that makes it root 5. So, root 5 is divided everywhere. So, also the root 2 here and root 3 here, and we want to implicit feedback from this. So, this is our y value, and we multiply it with the feedback matrix with this variable y, and we get this matrix. Now, going back, look, this was the average value of each, has to be with respect to each u, we are supposed to do it. So, you take this sum and take this sum divided by average, take the sum divided by average, and so on. So, the same manner in which we derived the update equation for SBD. Moving ahead with this, how many unknowns? Bi, Bu, Pi, Pu, Bi, M, this is N, this is how many? This is N cross K, this is M cross K, and this is also M cross K. Okay, 2 vectors are getting added. So, element wise element they will be getting added. Okay. So, this many parameters, and with respect to the way we did this one, for each of the variables we are supposed to now find out the updates. So, once you find out the updates, you will be getting this, and you will again run stochastic gradient descent to determine, start with certain random value and keep on iterating till your final criteria, stopping criteria is met. Now, that was the feedback which was getting generated from that rating matrix, and from rating matrix, why it was called the feedback from the rating matrix? Because our observation we made was whenever the rating was given, which means user is interested, give it 1, if the rating is not given, give it 0, and continuing in the same manner, if certain external rating matrix is external implicit feedback is available and treating it in a 1-0 manner, you will be getting this. In that case, it was a number of this value here, where did it, this value here, it was getting normalized by number of rating available on with respect to that particular item by user u. Here in this context, it is no more part of that, no more derived from that rating matrix. So, this number of it has no it has to now depend on the number of observations which is available from user u. This is not from the rating matrix. That is why that was actually the number of actual rating given by the user u. This is actually observed from another source. These are the references as usual, and all this content is derived from here. With this, we wind up. These are our conclusions. A typical collaborative filtering data exhibits large user and item biases. Baseline predictor models these biases. These baseline predictors can be improved by adopting user and item latent features conceptualized from your singular value decomposition, and this SVD based model enhances this baseline model, and it can be further enhanced by considering implicit feedback, and this implicit feedback can be derived from the rating matrix if it is not available from the external sources, and if it is available, then it can be added to improve the model performance. Now, these model parameters can be learned using the stochastic gradient descent. For this purpose, we have to take the error function, find out the partial derivatives with respect to each of the variable, and develop certain equations. So, which equations can be used to iteratively update these values starting from certain random values. Thank you.